Hey guys, it's Miss Johnson and I'm here to bring you the last part of our section 11.1 notes. Today we're going to cover a two-sided test and talk about how it relates to the confidence interval for a two-sided confidence interval of a mean. So the link between two-sided tests and confidence intervals for a population mean allows us to make a conclusion directly from the confidence interval. So if you construct a 95% confidence interval, constructing a 95% confidence interval for mu and it does not capture the null value, then we can safely reject the null at the 0.05 significance level. If you take a look at that 95% and that 0.05%, you should see how those two are related to each other. So your 95% confidence interval plus your alpha level equaling 0.05 is equal to 100 or 1.0. So that's how those two can be related. So it says if the 95% confidence interval for mu does capture the null value, then we should fail to reject. Okay. This is for a two-sided test at the 0.05 significance level. It says the same logic applies for other confidence levels, but only for a two-sided test. So if you did a 90% confidence interval, that corresponds to an alpha level of 0.1, where the two together would be 100% or a 1.0 type situation. So again, you can use that confidence interval in a two-sided test to make a judgment call of your null and alternative hypotheses. So we're going to look at an example here. It says at the Hawaii Pineapple Company, the mean weight of pineapples harvested from one large field was 31 ounces last year. A different irrigation system was installed in this field after the growing season. Managers wonder if this change will affect the mean weight of the future pineapples grown in the field. To find out, they select and weigh a random sample of 50 pineapples from this year's crop. So here's all the parts that we're going to look at. State an appropriate pair of hypotheses for the significance test in this setting. Be sure to define the parameter of interest, always. Check the conditions, okay? And then it gives you a confidence interval in part C. Confidence interval for the mean weight of pineapples grown in the field this year was that. Based on the interval, what conclusion can you make? And then can we conclude a different irrigation system caused a change in the mean weight of pineapples produced? Okay. So in part A, we're just going to do the state step here. Part A was state the appropriate pair of hypotheses. So we want to test the null hypothesis is that the mean is equal to 31 ounces. Our alternative would be that the mean is not equal to 31 ounces, because that was the point of the question. It says, managers wonder if this change will affect the mean. It doesn't say anything about being greater or less. Since it doesn't say anything about being greater or less, we simply want to test if it's different. That's it. Don't forget to state your parameter, where mu is the true mean weight in ounces of all pineapples grown in the field that year. So this is just simply the state step. If we were going to do a significance test on our own here without a confidence interval being present, this state step would be the same. So stating the hypotheses and the parameter, that's what we would put in our state step. The next one says check the conditions. So this is like the plan step, basically. But we don't even need to name the test here. They're not even asking for that. They just want us to check the conditions. So we're going to do that. Check our conditions. So for part B, the random, this was a random sample of 50 pineapples from the field, as stated in the question. From this year's crop. And then 10%, we can say it is safe to assume that 50 is less than 10% of all pineapples grown. Notice that they keep addressing the year, grown this year. They keep addressing this year because this is directly relating this current year to a previous year. So you really need to be explicit about what time frame you're looking at, which is why, you know, you've got that in a couple of areas. This year's crop, all pineapples grown this year, etc. And then large counts, this is an easy one this time, which is nice. We like it when our sample sizes are large. So n is equal to 50, which is greater than or equal to 30. So normality can be used. Normal calculations can be used. Okay, great. So our 3 conditions are met. Perfect. All right, let's take a look at part C. So now here's where we get into tying the confidence interval to a significance level and to the test with the hypotheses that we wrote. So here's the issue. The confidence interval that we have does not include 31. It starts at above 31 and goes up from there. So since it doesn't conclude 31, that gives us enough evidence to say that, yeah, that mean could be different. Okay, so that's how I'm going to state that here. The 95% confidence interval does not include the null. I should probably put ounces there, 31 ounces. Okay, so that means we have convincing evidence at the alpha equaling 0.05 level that the true mean weight in ounces of pineapples grown this year is not, this year is different from 31 ounces. Okay, so that confidence interval, the fact that that confidence interval does not include the 31, that is enough for us to say, yeah, our confidence interval doesn't include it. We're 95% confident that the mean falls in that interval. It's the 31.255 up to 32.616. So if we are confident enough that the mean falls into that interval at the 95% level, that means that at the 0.05 level, we can reject the null because we're 95% confident that the mean's in a different region. The mean falls in a different interval. So that's how that connection can be made. Now, this is only something that we can do with a two-sided test because we have to include both tails in that. And that's not something that happens when we do a one-sided test. When we're looking at a one-sided test, we're only looking at one tail. So when we're looking at both tails, now we can use that confidence interval to our advantage and tie it to a significance test. So let's talk about part D. Part D says, can we conclude that the different irrigation system caused a change in the mean weight of pineapples produced? Explain your answer. So here's where you have to be a little bit careful. Now, our significance test allowed us to reject the null. The confidence interval did not include 31, so we have significant evidence to say that the mean is truly not 31. It's something different. However, we did not do an experiment in this setting. We did not test the current irrigation system against the new irrigation system. So while we can say, yeah, the mean value is different, in this case, we think the mean value is higher. The 95% confidence interval is above the previous mean. So we can confidently say that the true mean is different, but remember that correlation does not mean causation. So just because this year's crop has a higher mean than last year's crop, we cannot successfully say that it's due to the irrigation system. So here's where you have to be really careful, okay? This is kind of an evil test maker trick. Your true answer here is no. This was not a randomized experiment. So because it was not a randomized experiment, we cannot infer causation. So there's a whole lot of other factors that could be responsible for causing the pineapples to change weight. So something along the lines of, it is possible that other factors than the irrigation system caused the change. And you can even give some suggestions such as water, weather, equipment, etc. Okay. So again, being very careful to not imply causation when it doesn't exist. We talked way back in chapter 2 about how it's really hard to establish causation. It's very easy to see correlation. Correlation is often present, but just because two things are correlated doesn't mean that one causes the other. So that's where we have to be really careful in a setting like this, because we did have enough evidence to reject the null, but we didn't run an actual experiment where there was a control group and a treatment group. So we cannot say that one thing caused the other. All right, so this is where we have to be careful about using tests wisely. It says statistical significance and practical importance, okay? Statistical significance is not the same thing as practical importance. To help practical importance, give a confidence interval for the parameter in which you are interested. Confidence intervals are not used as often as they should be, whereas significance tests are perhaps overused. So what we're saying here is, what they're talking about is the difference between that confidence interval and rejecting the null of the test. So if you had tested the mean of 31, you may have found enough evidence to reject that null. Okay, so then you say, yeah, we have enough evidence the mean isn't 31. We know it's not 31. We tested it and we found that we had to reject the null. Okay, great. But does that have a lot of context with it? When you give a confidence interval and say, we think our confidence interval of the true mean falls between these two values, that gives you a lot more context to the question, to the task at hand. That gives you a lot more meaning than just saying, nope, it's not 31. When you say, nope, it's not 31, that means it could be 35 or 38 or 40. When really, if you give a confidence interval, then you at least give a window of where that true mean could be. So that gives you a little bit more practicality of, well, what is the mean weight? Okay, because that's going to be more important perhaps in this setting than just saying, nope, it's not 31. So using that confidence interval to your advantage is often something that is underused. It's ignored. So that's an important thing, especially in this setting. That might make a difference in the equipment they use, in the staff they hire, depending on, is it a mean of 32 or is it a mean of 40 ounces? That causes a big difference. It causes a change in how you run your practices. So that confidence interval can be really valuable, and it's often underused. Then the second little tip here, it says beware of multiple analyses. So searching data for patterns is certainly legitimate. Performing every conceivable significance test on a data set with many variables until you obtain significantly A statistically significant result is not. This unfortunate practice is known by many names, including data dredging or p-hacking. So there's a lot of people, I've heard of p-hacking quite a bit. There's a lot of companies that will just say, oh, the test we just ran didn't give us enough evidence to reject. Well, we must do it again. So then they alter things. They do a different sample. They change their alpha value. They'll keep digging and keep digging and keep digging and go back and back and back. And if you're doing that too often just to get a p-value that allows you to make a result you want, that doesn't really have a whole lot of validity. And that's where we say, you've heard me say it before, 99% of statistics are inaccurate. Well, that's because people can manipulate them however they want. You change your p-value, you change your confidence level, you do all those things. You go back and get a different random sample. You got to be careful about repeating all these processes a lot and just redoing the steps and redoing the steps and redoing the steps. You lose validity when you do that. So that's kind of what they're getting at in this part. Okay, these two little tips are not really anything. This isn't like a definition that you have to know for the AP exam. It's just really a practical connection to make to the real world. Not everything that happens in our statistical analysis is something that's practical to carry out in the real world. So you just have to be mindful of that. All right, so that takes us to the end of section 11.1. Welcome to significance tests for means. We have one more section to talk about in chapter 11, so thanks for tuning in, and I will catch you next time.